I'm going to give a couple more examples of verifying trig identities. It's a couple different methods than the simple substitution method. My first problem is going to be sine of theta divided by tangent theta plus cosine theta divided by cotangent theta is equal to sine theta plus cosine theta. I'm going to work this problem on the left side only and write my reasons for each step on the right side. The first thing I'm going to do is, I know I want just a sine and a cosine, so I somehow have to get rid of this tangent and cotangent. And I'm going to replace tangent with quotient identity sine theta over cosine theta. So I'd have sine theta divided by cosine theta. And I'm going to replace cotangent theta with quotient identity cosine theta over sine theta. So for both of those, it's the quotient identity. When fractions are divided, you flip the second fraction, you flip the denominator, and it becomes a multiplication problem. So I'm going to take sine theta. Instead of saying divided by sine theta over cosine theta, it's the same thing as saying multiply cosine theta over sine theta. And then I'm going to flip cosine theta over sine theta and multiply by sine theta over cosine theta. So what I did was I divided fractions. Now when I multiply, sine divided by sine is 1. So I can reduce this by saying cosine theta, and then cosine theta divided by cosine theta is 1, so it's going to be plus sine theta. When all I did was multiply, it's also called the multiplicative inverse property. My final answer is supposed to be sine theta plus cosine theta, so I'm just going to switch the orders. It does not matter the order you multiply. So this becomes sine theta plus cosine theta. And that's the commutative property of addition. So that problem's done. The next problem I'm going to do is secant x minus secant x sine squared x. And that's going to equal cosine x. Since I have a secant x in the first term and a secant x in the second term, I can factor out secant x. So when I factor out secant x, I'm left with 1 minus sine squared x. So I factored actually a GCF. Then I can replace 1 with sine squared plus cosine squared using a Pythagorean identity. So I'd have secant x sine squared x plus cosine squared x minus sine squared x. And I use the Pythagorean identity. Sine squared plus cosine squared minus sine squared is going to equal just cosine squared, because when you add a sine squared x and a negative cosine squared x, it's 0. So I'd have secant x multiplied by cosine squared x. You could say combined like terms, simplified. I'm going to say that it's the additive inverse property. Once again, keep looking back to what I want to get to. I want to get to cosine x, and I'm almost there. Secant x is going to be 1 over cosine x, and it's being multiplied by cosine squared x. So I use the reciprocal identity to replace secant x with 1 over cosine x. Now when I multiply 1 over cosine x times cosine squared x, I'm left with cosine x. And that is a multiplication. You could break it apart and call it also the multiplicative inverse property. So that one's done. One more example on this video I'll show you. It deals with higher level factoring. I'm going to take cosine to the 4th of theta minus sine to the fourth of theta, and set it equal to 1 minus 2 sine squared theta. Since I want to get to something squared and I've got something to the fourth power, I look at this and I recognize it as a difference of squares. A squared minus b squared is going to equal a minus b, a plus b. So cosine of the fourth theta minus sine of the fourth theta is going to be cosine squared theta minus sine squared theta multiplied by cosine squared theta plus sine squared theta. And I factored a difference of squares. Cosine squared theta plus sine squared theta is the same thing as sine squared theta plus cosine squared theta, and that's equal to 1. So I've got cosine squared theta minus sine squared theta multiplied by 1 using the Pythagorean identity. When I multiply anything by 1, it's itself. So I'd have cosine squared theta minus sine squared theta, and that's the multiplicative identity property. Then I look at this, I'm close. I want to get rid of the cosine squared theta. So I do know that sine squared theta plus cosine squared theta is equal to 1. So if I solve that for cosine squared theta, I know that cosine squared theta is equal to 1 minus sine squared theta. So I'm going to replace cosine squared theta with 1 minus sine squared theta. And that's the Pythagorean identity. Now I have two of these. There's a negative sine squared theta here and a negative sine squared theta here, so I'm going to have 1 minus 2 sine squared theta, and all I did was combine like terms, or I added the two negatives. And that one's done.